Okay, welcome back. This is the second session of EDS 521, Educational Statistics. And tonight we're going to pick up where we left off, which is really in looking at the difference between descriptive versus inferential statistics. And we're going to talk a little bit tonight about central tendency and variation. I know that these are topics that are reviewed for the majority of the students in the course and are very elementary in nature. But that being said, that doesn't mean that they're not particularly important, because they are. As we get further into the course, we'll be much more focused on looking at hypothesis testing and looking at different ways of calculating the significance of differences between sets of numbers. But inherent in those kinds of calculations and comparisons are the patterns and the trends and the underlying scores. Inherent in inferential statistics are the kinds of patterns of data that we see in terms of the central tendency and the variation in the scores. And these underlying characteristics of our data are particularly important for us to focus on and to portray graphically and to examine carefully before we begin any kind of formal hypothesis testing. Because descriptive statistics are so elementary and so simple, it's easy for us to dismiss them as being unimportant. But nothing could be further from the truth. The underlying information, the underlying data, is everything. All of your inferential statistics and all of your hypothesis tests that we'll do later are based on the veracity or the truthfulness of those underlying scores. So it's critical for us to have a careful consideration of how central tendency and how variation plays out in sets of data, and the kinds of things for us to look for. So let's go on. Remember last time I talked about a substantive question leading us to a statistical question, which in turn leads us back to a statistical conclusion, and then finally to our substantive conclusion. And the example that we used last time was whether mathematical problem-solving ability was related to spatial reasoning ability. So there's our substantive question. And again, do scores on that mathematical problem-solving ability test correlate positively with scores on a spatial reasoning test? So there's our statistical question. There's something that we can actually explore with numbers. Finally, we can come to a statistical conclusion. Is there or is there not a statistically significant correlation between mathematical problem-solving ability and spatial reasoning scores? We find that there is, and then we can come to a substantive conclusion. Mathematical problem-solving ability is related to spatial reasoning ability. This circle, leading us from our substantive question all the way through to our substantive conclusion, all the way along here, it's critical to remember what is the purpose or what is the point in our conducting particular statistical tests. Sometimes we get waylaid by thinking about how interesting the statistics are, by what kinds of tests we can run, and all of the interesting things that we can do with our numbers. But it's easy then to get a little off track, to lose our focus on what's actually important. And the important thing is, what is it that we're trying to test? What does it show? And how does it help us understand our information better? So, some measures of central tendency. If we think of this as the average, and we ask the typical person on the street, we might say, what is the average? And chances are they'll talk to you about the arithmetic mean. That is, that they'll add up a series of numbers, and they'll take the average score across those numbers by dividing by the number of cases. This is what we tend to think of since grade school in terms of what is the average, the mean. But that's only one kind of average. We know that the average characterizes the typical score in a distribution, and so in fact we see that there are three kinds of averages. We have the mode, the most common score, the median, which is the central score, and the mean, which is, as I just described, the arithmetic average of a series of numbers. So, more formally put, the mode is the most frequently obtained score in a distribution. The median is the middle score in the distribution. It's also known as the 50th percentile. And the mean, of course, is the arithmetic average. So let's look at this small set of numbers. We have 2, 2, 4, 7, and 15. The mode, you should know. The median, again, you should know. The mean, maybe a little harder to calculate in your head, but let's skip ahead. The mode, of course, is 2 because we have two values that are that same value of 2. That's the most common score. The median is 4 because it's the central score. As we put all of our scores in ascending order, it's the score in the middle. And the mean, of course, is 6. And notice here that I put 6 what? It's 6 words correct on average on the vocabulary tests. Again, it's extremely easy to lose track of what it is that the numbers stand for. Always relate your data back to what it represents. 6 what? 4 what? As we start thinking about doing more inferential statistics later in the course, we're going to find that we'll run into a series of different mathematical symbols. Most of you will be very familiar with these, but some of you perhaps have not seen these before, so I will quickly just point out what these are. So this first value, this first symbol here, x bar, is the notation for mean. Now, it's not commonly used in journal articles. It's actually usually just the capital letter M. This Greek letter, sigma, actually stands for the sum of, and when you see that in notation like this, it means the sum of whatever follows it. So in this case, we have the sum of x, and x in this case are the scores in our distribution. Now, notice that this is all over n, which is the number of cases in our distribution. So n, when you see this, represents the n of a sample. And the reason that you know this is the n of a sample is that it's in italics and it's lowercase. If you see an uppercase n, that's an n representing the distribution, the entire population, excuse me, of our whatever population that we're thinking of. So if you see a capital N for boys in the state of Maine in public school, then that would represent all boys in school in K-12 education in the state of Maine. If you see a lowercase n in italics, that's some sample of boys within the larger population. The three kinds of central tendency are affected by extreme scores in different ways. Now, the modal score is simply the most common score. Now, the only way that the modal score can be affected by an extreme score is if that extreme score becomes the new modal score. The median score is relatively unaffected. It's going to move, but it's only going to move maybe one place by adding one more extreme score. The mean, however, is significantly impacted by extreme scores in a distribution. So let's take a look at how that plays out. So we know that from before, our mode here was 2, and our median was 4. And we see in this distribution of 2, 2, 4, 7, and 15, which has a mean score of 6, that we see what the relationship is among these numbers. Now, let's make some changes. The mode and the median are not sensitive to whether that score is 15 or 15,000 or, for that matter, 15 million. However, we know that the mean, the arithmetic mean, in this case is the sum of all scores divided by n. So in this distribution, the sum of scores is 30 divided by n. In this case, it's 5. Therefore, our mean is 6. However, what happens when we substitute that score for 15,000? Now, the sum of our scores is 15,015 divided by 5. So our mean is going to change radically, although our mode and our median, in this case, don't change at all. So, in the book, it talked about the algebraic property of the mean. That is, that the sum of all deviation scores is 0. And at first this may seem counterintuitive, but it makes complete sense. If someone's average, that means that they're precisely at the balancing point of all scores that are above them and all scores that are below them. If you were to take all the scores of the distribution and you were to take the average score, all the scores above that average score minus all the scores below that average score, the differences from the average would always equal 0.
Okay, so just to demonstrate this very quickly, again, the idea that the sum of deviation scores is always 0, consider this. We have the following numbers: 2, 3, 4, 5, and 6. The sum of these numbers is 20, and the mean is 20 divided by n of 5, which is 4. So recall that the sum of deviation scores, that is, the sum of x, the observed score, minus x bar, the mean, is always 0. So 2 minus 4 is negative 2, 3 minus 4 is negative 1, 4 minus 4 is 0, 5 minus 4 is 1, and 6 minus 4 is 2. And the sum of those deviation scores is 0. So it matters not what distribution you have, what set of numbers you have, but the deviation scores that you observe will always sum to 0. Okay, let's go on to the next part.
What is the relative location of the mode, the median, and the mean in a distribution? Well, in a normal distribution, we would expect that these all fall where? At the center. They all converge in the middle of the distribution. However, most distributions that we see in educational research aren't perfectly normal. In fact, most of our distributions of scores, say of test scores, tend to be skewed, and many of them tend to be negatively skewed. That is, that most of the scores are higher. So let's take a look at 2 or 3 examples here. So if we look at our first question mark up here, what is this score? This bar is the highest bar, which means that there are the most of the scores at, say, looks like it's about 7 or 6, somewhere in that range. And that score happened the most frequently. That is, this score is the middle score of our distribution. Therefore, it is and finally, this score is the average score of our distribution. You guessed it correctly, I'm sure. The mode is our most frequent score, the median, our middle score, and the mean is our arithmetic average. If we flip this distribution around, we find that the converse will be true. One of the things that I think is important for you to remember when we bandy about the word average is that we can choose the average that we want to report. Is it the mode? Is it the median? Is it the mean? And what do those 3 averages represent when we portray them? The idea that things are average is also somewhat of a misnomer. The idea that there is the average person or the average score, the average salary, is simply the arithmetic mean of all salaries. But in fact, we know that central tendency, or that concept of being average, is really just a hypothetical quality, whereas variation, or the idea that scores are not all actually in the middle, is the reality. So, what are some measures of variability? Well, variability refers to the amount that scores vary around some central point in the distribution. In this case, it's around the mean. One measure of variability is the range. And the range, as you read in your book, is simply the lowest score to the highest score in a given distribution. The interquartile range, which is something that you won't run into too often in reading research, is from the 25th percentile to the 75th percentile of all scores in the distribution. So, if we think about quartiles and the interquartile range, it's between the second and the third quartile. It's the second and third quartile. The lower end of our crude range, which is our minimum score, and the upper end of our crude range, which is our maximum score, represent our total range of our distribution. And of course, at the middle, between our second and third quartiles, we have the 50th percentile, which in a normal distribution like this one is also the modal score and it's also the mean score. Another way that we can portray variation around a mean is a box plot. Now, a box plot is nothing more than a graph that shows both central tendency and variability. In it, we see the median, we see where the first and the third quartiles set in the distribution, and we see the total range of scores. Once you know how to read a box plot properly, it's a very informative way to portray data. So, for example, here are some box plots of some scores from 11th grade Wyoming kids. Now, in this you'll see that our range goes from approximately 200 to approximately 280. Our median is noted with the black bar in the middle of the red box. And the red box shows us the range of the middle 50% of all kids that took the test. Here's another graphic portrayal of box plots, this time putting a number of different kinds of subtest scores together on the same graph. So study this for a moment, and then I want to ask you a couple of questions. Pay in particular attention to this box plot, say, versus this box plot. Okay. Now, if you didn't have time enough, you can just kind of rewind a little bit and you can pause and look at this some more. But I want to ask you a couple of questions. As you look at this, which is analyzing narrative elements of the story, and you look at, say, this one, which is critiquing supplemental ideas, what would you say about the overall performance of the interquartile range? Well, notice that the upper end of the interquartile range for analyzing narrative elements is lower than the lower point or the bottom of the interquartile range. This is the 25th percentile right here for critiquing supplemental ideas. So if we were to start to draw some inferences based on this box plot, by studying it a little bit, we can see the significance of the differences, or we can at least get some hint about the significance of the differences in our scores. So when we see two distributions that are largely overlapping, we see median scores that are slightly different. We see that the variation in this distribution, the red, using contextual clues, is somewhat smaller than in the green, which is analyzing themes. This is more variability. We can start to get a sense of how is the distribution, or how is the set of scores dispersed around the mean? Did everyone get about the same thing? Or was there a much broader range of performance in the set of scores? So, again, take a look at this and tell me, well, tell yourself, which one of these has the smallest amount of variation? And then which one has the largest amount? Okay, so if you chose analyzing narrative themes as having the smallest amount of variation, I would agree with that. It might be this blue one here, which is summarizing connections in text. Also, relatively little variation in the interquartile range. In other words, there was all the students did approximately the same, or closer to the same, than did, say, all of the students in analyzing themes. Here you see the interquartile range, as reflected in this box plot, is much bigger. So, very simple device, but a box plot is incredibly informative, and a set of box plots like this can give you a great deal of information if you stop and you really study the differences. They can give you a good starting place for the kinds of inferential statistics that you might want to do later. So, again, the question is, how does the box plot reveal the underlying shape of the distribution? Well, here's a couple of other ideas for you. This box plot that we pointed out, applying multi-step directions, as you can see, is a negative skew. That is, most of the kids did pretty well. Most of the scores in this distribution are not in the middle of it, but rather towards the top end. Whereas analyzing narrative elements, this was the score that they did particularly poorly on this year, is a positively skewed distribution. That is, that the tail of the distribution extends to the right, and most of the scores in this case were lower than the average. Okay? So our modal score, which is going to be down here even below our median score, remember, is lower than our average score. So what is variance? Well, variance, expressed as S squared, is nothing more than the sum of all deviation scores squared divided by the number of cases. Pretty simple. So the key term here is the deviation score. It's the score minus the mean. So our numerator, which is the sum of squares, is the sum of our squared deviations. So in this case, we take all scores, we subtract the mean from each score, and we square those scores. It's the sum of all of those squares. And for short, we call this the sum of squares. It's also signified in notations by SS. So variance squared is sum of a square over the number of cases. So to illustrate this better, let's just kind of walk through calculating the variance. So let's go back to a simple distribution. We've got 5, 5, 8, 9, and 13. 8 is our mean in this case. We remember, or we recall, that the variance is our sum of our deviation scores. That is, that we take each individual score that a child earned, and we subtract from it the mean. Okay? We subtract the mean, and then we square that. And we do that for all of our scores. We then divide those by the number of kids, in this case, or the number of cases that we have. So let's walk through it. 5 minus 8 squared is 3, and 3 squared is 9. Again, 5 minus 8 is 3, 3 squared is 9. 8 minus 8, which is our mean, is 0, 0 squared is 0. 9 minus 8 is 1, 1 squared is 1, of course. And 13 minus 8 is 5, and 5 squared is 25. So the sum of our squared differences, in this case, is 44. 44 divided by 5, so 44 goes here, 5 goes here. The average of that, then, is 8.8. That's our variance. But 8.8 what? Is the question. Well, variance is our method that we have to use to get to a much more important statistic, which is the standard deviation. Now, the standard deviation is the square root of our variance. So standard deviation, or S, is the square root of S squared. So if we unsquare, if you will, our variance, we now have our standard deviation. Now, in this case, it's 2.97 what? And that's always a key question. So let's go back to our previous slide. And what is it that we're measuring? The number of words correct. So on average, the students in this distribution scored 2.97 words correct is the average distance or difference from the mean score. Now, if you can't get your head around this just yet, as mentioned in the book, don't fret about it too much. We're going to walk through the procedural aspects of standard deviation. But if you take away this message that the standard deviation is the average distance that each person in the distribution or each score in the distribution was from the mean score, the average score, you'll have taken away the right message. The variance and the standard deviation are more sensitive than is the range. In other words, we can tell a lot more about a distribution by looking at the average dispersion versus the total dispersion. Although we might have one student who was doing nothing that day and got one problem correct, and we had another student who was a brainiac and got all 100 problems correct, perhaps the average student, if you will, wound up with more like 80 problems correct. So we can't see that from the range. The range merely shows us what the lowest score and the highest score was, whereas the variance and the standard deviation show us what was the average difference from the average score, if that's not too many averages in one sentence. So here's 3 distributions of 5 scores each. So look at distribution A. We have the scores of 1, 3, 5, 7, and 9. Distribution B, we have 1, 4, 5, 6, and 9. And distribution C, we have the values of 1, 5, 5, 5, and 9. So what's the median for each of these distributions? What's the mode for each of these distributions? And then finally, think about what is the average. Well, in the case of the first distribution, we don't really have a mode because we have only one score for each. But our median score is 5 and our average score is 5. In the second distribution, again, our median score is 5 and our average score is 5. Again, we don't have a mode because we only have one of each. And in the third distribution, our median score is 5, our average score is 5, and our modal score is 5. However, these 3 distributions are quite different in their average dispersion, or the standard deviation. In the first distribution, the sums of squares is 40. We have, in essence, sort of maximum distribution here. We have scores that are equally distributed, and we have extreme scores across our entire distribution. So our sums of squares, in this case, is 40, and our standard deviation is 2.83. In our second distribution, notice that our 3 scores are clustered closer to the mean. Now our sums of squares is smaller, and so is our average distance from, or our average difference from, the mean score. So in this case, our standard deviation is just 2.61. And then finally, notice that we have our sums of squares is just 32 here, because even though we still have these 2 extreme scores, all of our other scores are stuck on this modal score and our median score of 5. And we have, thus, a smaller standard deviation of 2.53. So what are some of the uses of standard deviation? Well, it's the most interpretable measure of variability. In other words, it gives us a sense of what was average, and then approximately how far from average did people score. It shows us something about the relationship between the standard deviation and the area under the normal curve. We'll get to that more later. And we can also use it to characterize consequences of sampling variation or statistical inference. In other words, we can use standard deviation to help us to determine what kind of sampling variation we can expect and what kinds of limits we have to set around our statistical inferences. And then finally, we can use standard deviation as a central component of determining the magnitude of a difference in 2 observed values. So if boys, say, score lower than girls on a reading test, how much lower, and the standard deviation, or the pooled standard deviation in the case of the effect size, as we'll see a little later, tells us how big that difference was in terms of the average distance that people scored from the mean. So that takes us to effect size, and we often look at did boys do better or worse than girls. So if in one case we see that the mean of boys minus the mean of girls equals plus 36, is this difference big? Is it big if it's the annual salary for first-year teachers in Maine? It's $36, a big difference, for example. Is it a big difference if it's measuring 5th grade kneecap scores on a scale of 501 to 580? Do you draw the same conclusion? And again, it all comes back to the underlying metric. What is it that you're measuring? What is it that is the question of importance? The standard deviation reflects the underlying scale of the distribution. A difference of $36 versus a difference of 36 kneecap points. Now, if you look at the average income of teachers in Maine, $36 is not going to be a large difference between two people's annualized incomes, where they total into the tens of thousands of dollars. But on an 80-point scale, 36 kneecap points is a much bigger difference because the average distance from the mean on the kneecap is much smaller than the average difference in dollars that we would expect to see between salaries of teachers. So let's try seeing this with a picture. Another way to think about effect size and to think about the magnitude of the differences in two distributions is to look at some different graphics that show the shapes of distributions. If we have distributions with medium variability, and that is something that is more akin to the normal distribution you may have seen in a number of different graphics, we can see that the degree of overlap is moderate. We have some boys who are scoring worse than some of the girls here in green. We have some of the girls who are scoring better than some of the boys here in blue. But for the most part, we have girls, in this case, scoring on average lower than boys. And we can see that the amount of area that is overlapping is relatively limited, but there's still some overlap. If there's a lot of variability, that is that the scores are extremely spread out, the same magnitude of difference, the same actual underlying value of that 34 points or the $26 is much less in some ways because we have many more boys that are overlapping with our girls. And likewise, we have many girls that are overlapping with the score distribution of our boys. In our third distribution, we have the same magnitude of difference. This is the same raw score point difference between our girls and our boys. But in this case, there's almost no overlap. Notice here, this is our only point of convergence, our only point of overlap. There's just a very few girls that are doing better than our boys, or vice versa. We can also think of this in terms of an effect size formula. Effect size is the mean of our first distribution minus the mean of our second distribution divided by the sums of squares from our first distribution plus the sums of squares from our second distribution. And that in turn is divided by the n of our first distribution plus the n of our second distribution. And we then take the square root of that. Now, this is our formula for standard deviation. So what we're doing is we are weighting or we're adjusting this formula for the differences in the sums of squares and the underlying size of the distributions for our two samples. So when we combine these, we wind up with variance pooled, or standard deviation pooled, excuse me. So if we were to substitute in here some annotations, we see that sums of squares is the sum of our deviation scores, of course. Okay, so we have, remember, sums of squares and an n for each of our groups, our boys and our girls. And what we wind up with in the bottom is our averaged standard deviation, our pooled standard deviation. So, if we think of this as 8th grade kneecap scores, we can see that our effect size is our first distribution, say boys, minus girls. We see that that difference was 36 points, divided by our pooled standard deviation, which for the kneecap is probably about 12 points. That is an effect size of +3. That is enormous. It's off the charts. But if it's the annual salary for first-year teachers in Maine, where we have $36 of difference, and our pooled standard deviation is $5,000, which is probably about right, but I made it up. Now our effect size is plus 0.0072, which is infinitesimally small. Effect size is a proportion of the pooled standard deviation. That is, again, it is the relationship of the difference that we see in our two distributions divided by the pooled standard deviation of those two distributions. So if 36 is a large proportion of our pooled standard deviation, then we're likely to have a large effect size. On the other hand, if our measured difference is a very small proportion of the standard deviation of our pooled distributions, then we're likely to get a very small effect size. So again, a number is simply not a number. In statistics and in looking at these kinds of comparisons and thinking about things like effect size, what's critical is to remember how these values tie back to the original metrics and the original purposes. So Cohen had some criteria for interpreting effect sizes. A small effect size, 0.20, that's 0.2 of one pooled standard deviation, or a moderate effect size, about half of a pooled standard deviation. A large, which would be 0.8 of one standard deviation, and we made this up, a wicked large one, which would be plus or minus one or more pooled standard deviations. So if you're coming up with differences of one or more pooled standard deviation units between your boys and your girls, it's very likely to be something very seriously wrong going on there. Either the girls are vastly outperforming the boys, or quite possibly, as you might have noticed in the chapter, you may have a data entry problem. So sometimes looking at these kinds of values, and when you see extremely large effect sizes, or you see extremely large differences between different distributions or different groups, it's a good indication that it might be time to go back and check your data. It's always a good thing to do, and it's always wise to plot your data so that you can see the effect of outliers.
Okay, so this week we've been looking at measures of central tendency, and in particular, the mean, the median, and the mode. And we saw that modal scores, or simply the most typical scores, were the most appropriate measures of nominal variables. Things like gender, religious preferences, or favorite flavor of ice cream are all best measured by the mode. It simply asks for what is the most frequent score. The median score, as we saw, is a statistic that helps us to look at a distribution that might be skewed in a more even way. For example, the example of income that we used, where the median score might be more indicative of what the common person, or the average, if you will, family earns for income, whereas the mean score tends to give us a sense that people are making a lot more money than is actually typically the case. The mean score, the one that we're the most familiar with coming into this, I'm sure, as we see, is a score that is largely influenced by extreme outliers. So in the case of the income, we saw that by adding one score that was extremely large, say that of an extremely wealthy person, that we drew a group's mean radically one direction. So when you think about measures of central tendency and you think about the sort of variability that's inherent in your data, I can't emphasize enough the importance of looking at the data that you're working with. The underlying characteristics of that, the nature of outliers that you may have, the extreme scores that are inherent in that data, the grouping of that data around some central feature, for example, a very narrow distribution. All of these things affect the way that you're going to interpret later kinds of inferential statistics about your data. So it's critically important that you graph your data, that you plot it, and that you examine these kinds of measures of central tendency carefully to determine whether or not you have a skewed distribution or you have a relatively normal distribution, and then what kinds of limitations your data may have. That's all for this time. We'll see you next week. Thanks.